Mercury's position and wide distance creates extremes. Mercury is the innermost planet of the solar system, orbiting closer to the Sun than any other world. From a distance, that single fact seems simple. But in reality, Mercury's position shapes every aspect of its existence. Its temperature, its surface, its gravity, its atmosphere, and even the length of its days are all controlled by how close it is to the Sunday. At its closest point, Mercury is less than 60 million kilometers from the Sunday. On a cosmic scale, this is an incredibly small distance. The Sun dominates Mercury's sky, appearing several times larger than it does from Earth. Solar radiation strikes the planet with intense force, delivering enormous amounts of energy to its surface. There is no other planet that experiences sunlight this directly, this consistently, and this violently. Yet proximity alone does not explain Mercury's extremity. What matters is not just how close the planet is, but how exposed it is. Mercury lacks the protective layers that shield other worlds. It has almost no atmosphere to trap heat, no thick clouds to reflect sunlight, and no oceans to distribute warmth. The Sun's energy reaches the surface almost unfiltered, striking bare rock that has been exposed for billions of years. As Mercury moves along its orbit, this exposure never truly eases. The planet travels quickly around the Sun, completing an orbit in just 88 Earth days. But its path is not a perfect circle. Mercury's orbit is stretched into an ellipse, bringing it significantly closer to the Sun at some points than others. This means the amount of solar energy it receives changes dramatically over short periods, intensifying temperature extremes even further. At its closest approach, Mercury receives nearly twice as much solar radiation as it does at its farthest point. On a planet with no atmosphere to soften these changes, that difference matters. The surface responds immediately. Temperatures rise rapidly, rocks expand, and the ground absorbs energy that it will later release into space just as quickly. Unlike Earth, Mercury has no system to balance this energy. There are no winds to move heat sideways, no clouds to block sunlight, no oceans to absorb and redistribute warmth. The planet exists in a state of constant thermal imbalance, heating rapidly when facing the Sun and cooling just as fast when darkness arrives. This imbalance begins with distance, but it is amplified by Mercury's small size. Mercury is only slightly larger than Earth's moon. Its gravity is weak compared to larger planets, making it difficult to hold on to gases. Over time, solar radiation stripped away whatever atmosphere Mercury once had. What remains today is so thin it barely qualifies as an atmosphere at all. Without air, heat behaves differently. On Earth, air traps warmth and slows temperature change. On Mercury, heat moves straight into the rock during the day and radiates straight back into space at night. The planet has no thermal memory. Each sunrise begins a rapid heating cycle, and each sunset triggers an equally rapid release of energy into the cold vacuum. The Sun's proximity also exposes Mercury to intense solar wind. Streams of charged particles constantly bombard the planet's surface, knocking atoms loose and eroding what little atmosphere exists. Over billions of years, this process has left Mercury stripped down to its most basic form, a world defined by raw exposure rather than balance. This relentless environment has shaped Mercury into a planet of extremes, not because it is close, but because it is unprotected. Other planets nearer the Sun might have developed thick atmospheres or reflective clouds. Mercury did not. Its small size, weak gravity, and early history left it defenseless, locked into a permanent struggle with solar forces. As we begin this journey, Mercury appears simple at first glance, a small, rocky world circling close to the Sunday. But beneath that simplicity lies a planet shaped entirely by proximity. Every extreme, we will explore every temperature swing, every surface fracture, every strange day-night cycle can be traced back to this fundamental fact. Mercury lives closer to the Sun than any other planet, and nothing stands between it and the full force of that star. Why being closest does not mean hottest. It seems logical to assume that the planet closest to the Sun would be the hottest. Distance feels like the most straightforward measure of temperature. Closer should mean warmer, farther should mean colder. But Mercury defies this intuition in a surprising way. Despite its proximity, Mercury is not the hottest planet in the solar system. That title belongs to Venus. This contradiction reveals one of the most important lessons Mercury has to teach. Temperature is not controlled by distance alone. It is shaped by how a planet holds and manages heat. Mercury's extremity lies not in constant warmth, but in violent contrast. During Mercury's long days, surface temperatures can soar above 400 degrees Celsius. The ground becomes hot enough to melt lead. Rocks glow faintly as they absorb solar energy. Any spacecraft exposed to direct sunlight must endure conditions more extreme than almost anywhere else in the solar system. Yet when night falls, Mercury becomes one of the coldest planets. Without sunlight and without an atmosphere to retain warmth, the surface loses heat rapidly. Temperatures plunge to nearly -180 degrees Celsius. In these regions, the cold rivals that of distant dwarf planets far beyond Neptune. This is the paradox of Mercury. It experiences both some of the hottest and some of the coldest conditions found on any planet, and it does so on the same surface within the same rotation cycle. Venus, by contrast, is farther from the Sun, but wrapped in a thick atmosphere composed mostly of carbon dioxide. That atmosphere traps heat efficiently, creating a powerful greenhouse effect. Once heat enters Venus's atmosphere, it has nowhere to escape. The result is a planet that remains hot day and night, pole to pole, with almost no temperature variation. Mercury has no such insulation. Its thin exosphere is composed of scattered atoms knocked off the surface by solar radiation. It cannot trap heat. It cannot circulate warmth. It cannot moderate extremes. Each location on Mercury exists almost entirely at the mercy of the Sun's presence or absence. This difference explains why Mercury's temperature profile is so extreme. It is not the average temperature that defines the planet, but the range. The swing between day and night is wider than on any other planet in the solar system. Even the Moon, which also lacks an atmosphere, does not experience the same extremes. Mercury's closer proximity to the Sun magnifies every effect. Daytime heating is more intense. Nighttime cooling is more severe. The cycle repeats endlessly, carving stress fractures into the crust and reshaping the surface over geological time. This constant expansion and contraction have consequences. Rocks crack, cliffs form, the surface slowly breaks itself apart under thermal stress. Mercury's environment is not just hot or cold, it is mechanically violent, driven by temperature extremes rather than impact alone. Understanding why Mercury is not the hottest planet helps us understand why it is the most extreme. Heat alone is not the measure of harshness. Instability is. Mercury exists in a state of permanent imbalance, unable to settle into thermal equilibrium. The Sun dominates Mercury's sky, but it does not provide comfort. It delivers punishment in cycles, blazing heat followed by deep cold, over and over again, for billions of years. Daytime heat hot enough to melt metals. When the Sun rises over Mercury's horizon, the change is immediate and unforgiving. There is no dawn glow, no gradual warming, no soft transition from night to day. Without an atmosphere to scatter light or slow the transfer of heat, sunlight strikes the surface directly, delivering energy with brutal efficiency. As Mercury turns toward the Sun, its surface begins to heat almost instantly. Temperatures climb rapidly, rising hundreds of degrees in a matter of hours. In the brightest regions near the equator, the ground can reach temperatures above 400 degrees Celsius, This is hot enough to melt lead, zinc, and tin. It is hot enough to weaken metal structures and fracture solid rock. The reason for this extreme heat lies not only in Mercury's proximity to the Sun, but in how the planet absorbs energy. Mercury's surface is composed primarily of dark, rocky material that readily absorbs sunlight. Unlike reflective clouds or bright ice, this rock does not bounce energy away. It drinks in solar radiation, converting light directly into heat. Once absorbed, that heat has nowhere to go. On Earth, warm air rises, winds carry energy away, and oceans absorb excess warmth. On Mercury, none of these processes exist. Heat remains trapped in the ground itself, building steadily as long as sunlight continues to fall. Compounding this effect is Mercury's slow rotation. A single day on Mercury lasts far longer than a day on Earth. The Sun moves slowly across the sky, lingering over the same regions for weeks at a time. This prolonged exposure allows temperatures to climb higher and higher, pushing the surface toward its thermal limits. The Sun itself appears enormous from Mercury's surface. It dominates the sky, blazing with intensity. Solar radiation here is several times stronger than what Earth receives. Every square meter of Mercury's surface absorbs far more energy than any rocky world farther out in the solar system. Even Mercury's lack of atmosphere contributes to heating in a subtle way. While atmospheres trap heat, they also reflect and scatter incoming sunlight. Mercury's near vacuum allows sunlight to arrive undiminished. Nothing softens its impact. Nothing diffuses its energy. As the ground heats, it expands. Rocks swell under thermal stress, pushing against each other. Over time, this repeated expansion creates fractures, cracks, and faults across the surface. Mercury's landscape is not shaped by water or wind, but by temperature itself. Spacecraft that have visited Mercury have measured these extreme temperatures directly. Instruments have recorded surface readings that fluctuate wildly depending on whether sunlight is present. These measurements confirm what physics predicts. Mercury's days are among the hottest environments any spacecraft has ever encountered. Yet this heat is deceptive. It does not penetrate deeply into the planet. Just a short distance below the surface, temperatures drop sharply. The rock does not retain heat for long. As soon as sunlight moves on, the energy escapes just as quickly as it arrived. This shallow heating explains why Mercury's interior remains relatively cool compared to its surface. The planet bakes on the outside, but the heat does not last long enough to sink deep. Mercury's extremity is skin-deep but relentless. Day after day, orbit after orbit, Mercury endures this cycle of intense heating. There is no moderation, no seasonal relief, no atmospheric shield. The planet exists in a state of perpetual exposure, absorbing the sun's energy with nothing to soften the impact. But as extreme as Mercury's daytime heat is, it tells only half the story. Because when the sun finally sets, Mercury becomes something else entirely. Nighttime cold, colder than distant worlds. When darkness falls on Mercury, the transformation is as sudden as the sunrise. Without sunlight, the surface loses its only source of heat. And without an atmosphere to trap that heat, the energy escapes straight into space. Temperatures plunge rapidly. Within hours, the ground cools by hundreds of degrees. The rock that once glowed with heat now radiates its energy outward, becoming colder and colder as the long Mercurian night stretches on. Eventually, temperatures can drop below -180 degrees Celsius. This is colder than many regions far beyond Mercury's orbit, colder than the surface of Pluto during its distant winter, colder than most objects that exist in the outer solar system. The reason Mercury becomes so cold is the same reason it becomes so hot. It has no atmosphere to regulate temperature. On Earth, air acts as a thermal blanket, slowing the loss of heat after sunset. On Mercury, there is nothing to hold warmth in place. Heat escapes through radiation, streaming away into the vacuum of space. The process is efficient and relentless. Every hour without sunlight pushes the surface closer to absolute cold. Mercury's long nights make this cooling even more extreme. Because the planet rotates so slowly, darkness lasts for weeks at a time. The surface has ample time to lose every trace of warmth gained during the day. By the time the sun rises again, the ground is deeply chilled. Rocks contract as they cool, pulling away from each other. The cycle of expansion and contraction repeats, weakening the crust over billions of years. This extreme cold affects Mercury's surface chemistry as well. Some elements become brittle, others behave differently under repeated thermal stress. Over geological time, these temperature swings have altered the planet's surface more thoroughly than erosion ever could. The cold also creates surprising refuges. In regions that never see sunlight, deep craters near Mercury's poles, temperatures remain permanently frozen. These shadowed areas never warm, even when the rest of the planet bakes. Here, ice can survive for billions of years, hidden just beneath the surface. This coexistence of extreme heat and extreme cold on the same planet is unmatched in the solar system. Mercury does not have a stable climate. It has a thermal pendulum, swinging violently between two extremes. No other planet experiences such dramatic temperature variation. Not Mars, not the Moon, not even airless asteroids show the same combination of proximity, exposure, and prolonged day-night cycles. Mercury's nights are not simply cold, they are deeply, profoundly cold, shaped by the complete absence of heat retention. Darkness here is not gentle, it is absolute. This constant thermal violence shapes Mercury in ways that go beyond temperature alone. It affects the planet's geology, its atmosphere, and even the way time itself behaves on its surface. Mercury's slow rotation explained calmly. On most planets, the passage of time feels intuitive. Days pass quickly, nights return regularly, and the rhythm of light and darkness creates a familiar cycle. On Mercury, time behaves very differently. Here, rotation and orbit are locked into an unusual relationship that stretches days into extremes and turns time itself into one of the planet's defining forces. Mercury rotates very slowly. One full rotation on its axis takes about 59 Earth days. This alone would make its days long and its nights equally extended. But Mercury's situation is even more unusual. While it rotates slowly, it orbits the Sun very quickly, completing a full journey around the Sun in just 88 Earth days. This combination creates a strange overlap between rotation and orbit. From space, Mercury spins steadily as it travels along its elliptical path. But from the surface, the Sun appears to move across the sky at an almost imperceptible pace. Days stretch into weeks. Sunlight lingers, holding the ground under constant heat for extraordinary lengths of time. On Mercury, a single sunrise to sunrise cycle, what we would call a solar day, lasts 176 Earth days. That is longer than 2 Mercury years. In practical terms, this means that once the Sun rises, it will not set again for nearly 3 months, and once it sets, darkness will last just as long. This slow rhythm magnifies every thermal effect. Heat is not delivered in short bursts. It is applied steadily, relentlessly, without relief. The ground does not have time to cool during the day, because the day does not end. Temperatures continue climbing as long as sunlight remains. Likewise, when night finally arrives, cooling does not stop after a few hours. It continues uninterrupted for weeks. The surface releases all stored heat, radiating energy into space until nothing remains to slow the descent into cold. This slow rotation is one of the primary reasons Mercury experiences the most extreme temperature differences in the solar system. On planets with faster rotation, even intense sunlight is balanced by frequent nights. On Mercury, balance never arrives. The reason Mercury rotates so slowly lies in its early history. When the planet formed, it likely spun much faster. Over time, the Sun's immense gravitational influence began to exert tidal forces on Mercury, tugging at its shape and gradually altering its rotation. Each orbit drained a small amount of rotational energy, slowing the planet bit by bit. This process unfolded over billions of years. As Mercury lost rotational speed, it settled into a stable pattern that minimized energy loss. But the outcome was not what intuition might expect. Mercury did not become tidally locked in the same way the Moon is locked to Earth. Instead, Mercury entered a more complex state, a state that would lock its rotation and orbit together in a precise and unusual way. The resonance that locks Mercury into extremes. Mercury exists in what scientists call a 3-to-2 spin-orbit resonance. This means that for every 2 orbits Mercury completes around the Sun, it rotates exactly 3 times on its axis. This ratio is stable, repeating endlessly, locking Mercury into a precise gravitational rhythm. This resonance is the result of the Sun's tidal forces acting on Mercury's slightly elongated shape. Mercury is not a perfect sphere. Its mass distribution allows the Sun's gravity to grip it unevenly, nudging its rotation into this specific pattern over immense spans of time. The result is a planet where time behaves asymmetrically. Certain regions of Mercury face the Sun at nearly the same point in its orbit, over and over again. These locations experience the most intense and prolonged heating, repeatedly exposed to sunlight when Mercury is closest to the Sunday. In these regions, the Sun appears to slow, pause, and even reverse direction slightly in the sky due to Mercury's elliptical orbit. From the surface, this creates an eerie effect where sunlight lingers longer than expected, further amplifying heating. The same places bake repeatedly, while others endure extended cold. This resonance ensures that Mercury's extremes are not evenly distributed. Some longitudes are punished more than others, subjected to repeated thermal stress across billions of years. The planet's surface remembers this imbalance, preserving scars that reflect this uneven exposure. Unlike Earth, where rotation spreads sunlight evenly over time, Mercury concentrates it. The resonance locks certain areas into predictable cycles of intense heat and deep cold. There is no randomness, no weather to redistribute energy, no atmosphere to blur boundaries. Time on Mercury is mechanical and unforgiving. This strange relationship between rotation and orbit also alters the experience of the Sun itself. From Mercury's surface, the Sun can appear to rise, stop, and move backward briefly before continuing its path. This phenomenon, while subtle, reflects the complex dance between rotation and orbital speed. These prolonged days and nights are not just curiosities. They define Mercury's identity. They explain why heat penetrates only shallow layers, why cold reaches so deeply, why the surface cracks and fractures repeatedly, why Mercury cannot hold an atmosphere. The planet is locked into a rhythm that exaggerates every physical process. Heat is never gentle, cold is never brief. Everything happens slowly, but with overwhelming effect. Why Mercury cannot hold an atmosphere? When we think of planets, we often imagine them wrapped in thick layers of air, clouds drifting, winds circulating, pressure holding warmth in place. Mercury does not have this. Instead, it exists almost completely exposed, with nothing substantial separating its surface from the vacuum of space. Mercury's atmosphere is so thin that it is often described as an exosphere rather than a true atmosphere. In this near vacuum, individual atoms rarely collide with one another. There is no pressure, no wind, and no weather in any meaningful sense. The planet does not breathe. It simply exists. The reason Mercury cannot hold an atmosphere begins with gravity. Mercury is small, only slightly larger than Earth's moon. Its gravitational pull is weak compared to larger planets like Earth or Venus. Gravity is what keeps gases bound to a planet, preventing them from drifting away into space. On Mercury, that grip is fragile. Even if Mercury once had a thicker atmosphere, it would have struggled to keep it. Gas molecules move constantly, and lighter ones can reach escape velocity if the planet's gravity is insufficient. Over time, Mercury lost much of its early atmosphere simply because it could not hold onto it. But gravity alone does not tell the full story. Mercury's proximity to the Sun makes atmospheric survival even more difficult. The Sun constantly bombards Mercury with intense radiation and streams of charged particles known as the solar wind. These particles collide with atoms near the surface, knocking them free and pushing them outward into space. This process, known as sputtering, slowly strips atoms away. Any gas that forms near the surface is quickly swept up by solar forces and lost. Mercury exists in a constant state of erosion, not just of rock, but of atmosphere itself. The planet's extreme temperatures worsen this effect. During the long daytime, heat causes atoms to move faster, increasing their chances of escaping Mercury's weak gravity. During the long night, the lack of heat prevents gases from accumulating in any stable way. The cycle never allows an atmosphere to rebuild. Volcanic activity may once have released gases from Mercury's interior, briefly thickening its atmosphere. But over billions of years, these gases were lost. The Sun's influence proved relentless, and Mercury's defenses were minimal. Today, Mercury's exosphere is constantly changing. Atoms of sodium, potassium, oxygen, and helium appear briefly before drifting away. Some are knocked loose by sunlight. Others are released by micrometeorite impacts. None remain for long. Mercury's atmosphere is not a blanket. It is a trace, a fleeting collection of particles that exists moment by moment, never building into anything stable. This absence of atmosphere is one of Mercury's defining extremes. It explains why temperature swings are so violent, why sound cannot travel, why the sky above Mercury is permanently black, even at noon. Mercury does not soften the Sun's presence. It absorbs it directly. How extreme conditions destroy atmospheric stability. On planets with atmospheres, temperature differences create movement. Warm air rises. Cool air sinks. Winds form. Heat is distributed. Mercury has none of this. Its environment does not circulate, it fractures. The extreme temperature differences between day and night prevent atmospheric stability from ever forming. Any gas released on the day side heats rapidly and expands. As it moves, it encounters darkness, cools, and condenses. The process is chaotic and inefficient, unable to create sustained pressure. Because Mercury rotates so slowly, gases cannot circulate around the planet before conditions change. On Earth, air moves around the globe in days. On Mercury, a parcel of gas would face weeks of direct sunlight, followed by weeks of darkness. The result is escape, not balance. Solar radiation further destabilizes the situation. Ultraviolet light breaks apart molecules, ionizing atoms and making them easier for the solar wind to carry away. This constant assault ensures that Mercury's exosphere remains thin and temporary. Mercury also lacks a strong global magnetic field to deflect solar wind. While it does have a weak magnetic field, it offers only limited protection. Charged particles can still reach the surface, directly interacting with exposed rock and liberated atoms. Over time, this exposure has permanently altered Mercury's surface chemistry. Elements that might otherwise accumulate in an atmosphere are instead implanted into the soil or lost to space. The surface becomes both source and victim, releasing atoms only to have them stripped away again. The absence of an atmosphere means there is no erosion by wind or water. Mercury's surface preserves ancient features, craters, and fractures that would have been erased on more sheltered worlds. Temperature, impact, and solar radiation are the only sculptors here. This exposed environment reinforces every other extreme we have already explored. Heat becomes harsher, cold becomes deeper, time stretches longer. Nothing intervenes to moderate conditions. Mercury exists in a state of permanent vulnerability. It is a planet where space touches the ground, solar radiation, and a surface under constant attack. On Mercury, the sun is not a distant presence in the sky. It is a dominating force, shaping the planet continuously and without rest. Every moment Mercury faces the sun, it is exposed to radiation far more intense than what any other rocky planet experiences. This radiation does not simply warm the surface, it alters it. Solar radiation at Mercury's distance is several times stronger than at Earth. High-energy ultraviolet light and X-rays strike the surface directly, penetrating exposed rock and loosening atoms from their bonds. With no atmosphere to filter this radiation, the surface absorbs the full intensity, enduring conditions that would quickly destroy unprotected materials elsewhere in the solar system. Over time, this radiation breaks down minerals at the surface. Chemical bonds weaken. Certain elements are preferentially lost, while others become concentrated. The surface gradually changes, not through erosion by wind or water, but through radiation damage. Mercury's ground is constantly being rewritten at the atomic level. Adding to this exposure is the solar wind, a continuous stream of charged particles flowing outward from the sunday. These particles move at enormous speeds and carry enough energy to knock atoms free when they collide with Mercury's surface. Each impact ejects particles upward, feeding the planet's thin exosphere and then sweeping them away into space. This process never stops. Every second, Mercury loses atoms to the sunday over billions of years. This steady loss has shaped the planet's composition. Light elements are especially vulnerable, stripped away long ago, leaving behind a surface enriched in heavier materials. The solar wind also implants particles into Mercury's soil. Hydrogen and helium become embedded in surface grains, subtly altering the chemistry of the regolith. The surface becomes both eroded and infused, a record of constant interaction with solar forces. Because Mercury lacks a thick atmosphere, there is no buffer zone. Solar particles strike the ground directly, carving microscopic scars into exposed rock. This constant bombardment darkens the surface and reduces its reflectivity, allowing it to absorb even more heat during the day. Unlike Earth, where solar radiation is moderated by air, clouds, and magnetic shielding, Mercury experiences space weather at ground level. The boundary between space and surface is almost non-existent. The sun's influence reaches all the way down. This relentless exposure explains why Mercury's surface looks ancient and worn, despite lacking erosion by wind or water. Radiation and particle impacts act as a slow, persistent form of weathering, reshaping the planet grain by grain. Mercury's proximity to the sun turns what would be a background process elsewhere into a dominant force. Solar radiation is not a distant energy source here. It is a direct sculptor of the planet itself. How the sun slowly reshapes Mercury. Beyond surface damage, the sun's influence reaches deeper, affecting Mercury's structure and long-term evolution. Heat and radiation do more than alter minerals, they drive mechanical stress that gradually reshapes the planet. Each long day heats Mercury's surface intensely. Each long night cools it deeply. This repeated expansion and contraction creates enormous stress in the crust. Over time, rocks crack, fault lines develop, and large sections of the surface shift. Mercury's crust has endured this cycle for billions of years. Unlike Earth, where tectonic activity and erosion erase stress patterns, Mercury preserves them. The planet's surface records its struggle with solar extremes in the form of fractures, cliffs, and compressed terrain. The Sun also influences Mercury's magnetic environment. While Mercury has a weak magnetic field, it is constantly compressed and distorted by the solar wind. On the day side, the magnetic field is pushed close to the surface. On the night side, it stretches far into space. This shifting field exposes large regions of the surface to direct particle impact. Over geological time, this interaction may have contributed to the gradual loss of Mercury's volatile elements. Heat drives them upward, radiation strips them away, gravity fails to hold them. The Sun slowly removes anything that is not firmly anchored to the planet. Even Mercury's shape bears the mark of solar influence. The planet is slowly shrinking as it cools internally, but surface stress from extreme heating likely accelerates the formation of large cliffs known as scarps. These towering features represent sections of crust forced upward as the planet contracts. The Sun does not simply shine on Mercury. It pressures it. It stresses it. It reshapes it. And it does so quietly, steadily, without pause. As we prepare to move into the next chapter, the consequences of this influence become even more dramatic. Beneath Mercury's battered surface lies an unexpected interior, one dominated by metal, heavier and denser than a planet of its size should be. Mercury's massive iron core. Beneath Mercury's battered surface lies one of the greatest mysteries in the solar system. For a planet so small, Mercury contains an interior that should not exist in its current form. It is a world dominated not by rock, but by metal. And this hidden structure is one of the primary reasons Mercury behaves so differently from every other terrestrial planet. Mercury's density is unusually high. When scientists first measured its mass and size, the numbers did not align with expectations. A planet as small as Mercury should be much lighter. Instead, it is nearly as dense as Earth, despite being far smaller in volume. This immediately suggested that something unusual lay beneath the surface. The explanation emerged gradually. Mercury possesses an enormous iron core, one that makes up roughly 85% of the planet's radius. In comparison, Earth's core accounts for just over half of its radius. Mercury's rocky mantle and crust form only a thin outer shell around a vast metallic interior. This means that if Mercury were hollowed out, leaving only its core behind, it would still resemble a small planet rather than a simple metallic center. No other rocky world in the solar system has such a disproportionately large core. This internal structure has profound consequences. Iron conducts heat differently than rock. It cools slowly and retains thermal energy deep within the planet. While Mercury's surface experiences violent temperature swings, its interior changes far more gradually, preserving heat accumulated billions of years ago. The core also plays a role in Mercury's magnetic field. Despite its small size and slow rotation, Mercury possesses a weak but global magnetic field. This is unexpected. Magnetic fields typically require a molten, moving metallic core and sufficient rotational energy. Mercury barely meets these conditions, yet its core remains partially molten. This molten region suggests that Mercury's interior is still active, at least at a slow pace. Heat trapped inside the massive iron core continues to circulate, generating a faint magnetic shield. While this field offers little protection from the Sun, its mere existence is remarkable given Mercury's size. The formation of such a large core raises difficult questions. How did Mercury end up this way? One possibility is that the planet formed from metal-rich material close to the Sun, where lighter elements were less common. Another theory suggests that Mercury once resembled Earth more closely, with a thicker mantle that was later stripped away. In the early solar system, violent collisions were common. A massive impact could have removed much of Mercury's rocky outer layers, leaving behind a metal-dominated core. Alternatively, intense solar radiation during Mercury's formation may have prevented lighter materials from accumulating in the first place. Regardless of its origin, the result is a planet whose behavior is governed by metal. The core's presence affects Mercury's gravity, its magnetic environment, and even the way its surface responds to stress. When the planet cools and contracts, the metal core plays a central role in driving global changes. Mercury's iron heart also explains why the planet has not completely solidified. The large core retains enough heat to remain partially molten long after a smaller or more rock-dominated planet would have cooled entirely. This lingering heat continues to influence Mercury's evolution today. In many ways, Mercury is less like a typical rocky planet and more like a metallic remnant, a survivor shaped by extremes both internal and external. Its core is not just a feature. It is the foundation of everything that makes Mercury unusual. But the presence of so much metal leads to another question. Why is Mercury so dense in the first place? Why Mercury is denser than it should be? Density tells a story about a planet's past. It reveals how much metal and rock it contains, how those materials are arranged, and what events shaped its formation. In Mercury's case, density tells a story of loss, exposure, and survival. When scientists compare Mercury to other terrestrial planets, its density stands out immediately. Only Earth rivals it. Yet Earth is much larger and contains far more rock relative to metal. Mercury's density suggests that much of what once surrounded its core is missing. One explanation is catastrophic impact. In the chaotic early solar system, collisions between forming planets were frequent and violent. A single, enormous impact could have stripped away much of Mercury's outer mantle, blasting lighter material into space and leaving behind a dense metallic core. This theory fits Mercury's environment. Close to the Sun, orbital speeds are high, making collisions especially energetic. Material ejected during such an impact would have been unlikely to fall back, either pulled into the Sun or dispersed into interplanetary space. Another possibility involves prolonged solar influence rather than a single event. During the Sun's early, more violent phase, intense radiation may have driven lighter elements away from Mercury as it formed. This process would have left behind a metal-rich planet from the start, rather than stripping it later. Some evidence suggests Mercury formed under conditions very different from those of Earth or Mars. Temperatures near the young Sun were extreme, potentially preventing volatile and rocky materials from condensing efficiently. Metal, with its higher condensation temperature, may have dominated from the beginning. Regardless of which process dominated, the outcome is the same. Mercury lost much of its original rocky envelope, leaving a planet unusually rich in iron. This loss reshaped Mercury's destiny. Without a thick mantle, the planet cooled differently. Without sufficient gravity, it lost its atmosphere. Without insulation, it became vulnerable to the sunday. The planet's high density also affects its gravity field. Mercury's gravitational pull is uneven, influenced by the distribution of its massive core beneath a thin crust. This unevenness influences orbital dynamics, surface stress, and even the way spacecraft move near the planet. As Mercury's core slowly cools, it contracts. This contraction forces the outer crust to compress and break, creating enormous cliffs that span hundreds of kilometers. These features are not the result of plate tectonics, but of planetary shrinkage driven by internal metal cooling. Mercury is literally collapsing inward, its surface wrinkling as the interior contracts. This process has been ongoing for billions of years and continues today at an almost imperceptible pace. The density that makes Mercury unique also ensures its endurance. A metal-rich planet resists complete disintegration. It survives solar bombardment, retains internal heat, and preserves a magnetic field long after other small worlds have gone silent. Mercury's density is not an accident. It is the signature of a planet that lost much, endured more, and settled into an extreme existence closer to the Sun than any other world. Mercury cooling and contracting from the inside. Mercury is not a static world. Although it appears quiet and motionless from afar, the planet has been slowly changing from within for billions of years. Unlike Earth, where tectonic plates move laterally and recycle the surface, Mercury's transformation happens inward. The planet is cooling, and as it cools, it is shrinking. All planets begin their lives hot. During formation, collisions, compression, and radioactive decay generate enormous internal heat. Larger planets retain that heat longer, insulated by thick mantles and active interiors. Smaller planets cool faster. Mercury, despite its massive iron core, is no exception. As Mercury's interior slowly loses heat, the metal core contracts. Iron shrinks as it cools, and because Mercury's core makes up such a large portion of the planet, even small temperature changes result in significant volume reduction. This contraction does not happen suddenly. It unfolds over millions and billions of years, almost imperceptibly slow, yet relentless. The rocky crust surrounding the core has no choice but to respond. As the interior shrinks, the crust is forced to adjust to a smaller planetary volume, but rock cannot simply compress smoothly. Instead, it breaks, buckles, and folds. The surface shortens horizontally, creating massive compressional features that permanently scar the landscape. These changes do not occur evenly. Stress accumulates in certain regions until the crust finally gives way. When it does, enormous sections of the surface are pushed upward and over neighboring terrain. The result is a network of cliffs, ridges, and faults that stretch across vast distances. Unlike Earth, Mercury has no plate tectonics to redistribute stress. There are no moving plates, no recycling of crust, no mantle convection driving surface renewal. Every bit of contraction must be absorbed by the crust itself. This makes Mercury's surface a direct record of its internal cooling. Measurements taken by spacecraft have allowed scientists to estimate how much Mercury has shrunk. The numbers are striking. Over its lifetime, Mercury's radius may have decreased by several kilometers. That may sound small, but on a planetary scale, it represents enormous internal change and tremendous surface stress. This contraction has been ongoing since Mercury's early history and continues today. The planet is still cooling, its core is still losing heat, and its surface is still responding, even if the process is now extremely slow. What makes Mercury unique is not simply that it is shrinking, but how clearly that shrinkage is written across its surface. On many planets, erosion, volcanism, or tectonics erase evidence of early processes. On Mercury, nothing hides the scars. The planet's lack of atmosphere and geological recycling preserves every fracture, every fold, every compressed ridge. Mercury's shrinking also affects its magnetic field. As the core cools and changes state, the movement of molten metal shifts. This alters the strength and structure of the magnetic field over time, contributing to its weakness and instability compared to Earth's. The cooling process also interacts with Mercury's extreme surface temperatures. Repeated heating and cooling cycles stress the crust from above, while internal contraction stresses it from below. The planet is pulled apart and squeezed together simultaneously, amplifying structural weakness. In this sense, Mercury exists under constant tension. The sun heats it, space cools it, the core contracts it, the crust fractures in response. No other rocky planet experiences this combination of internal and external stress to such a degree. Mercury is not just old. It is tired. A planet slowly tightening its own shell as it cools from the inside out. And the most dramatic evidence of this process rises thousands of meters above the surrounding terrain. Giant cliffs formed by planetary collapse. Scattered across Mercury's surface are towering landforms unlike anything seen on most other planets. These features are not mountains formed by volcanic uplift or plate collision. They are cliffs, vast, steep scarps created when the planet's crust was forced to break and overlap as Mercury shrank. Some of these cliffs stretch for hundreds of kilometers. Others rise more than a kilometer above the surrounding plains. From orbit, they appear as long, curving walls casting sharp shadows across the landscape. From the surface, they would look like immense stone ramparts, frozen in place for billions of years. These scarps formed when compressional stress exceeded the strength of the crust. As Mercury's interior contracted, the outer shell became too large for the shrinking core. The crust responded by breaking along faults and pushing slabs of rock upward and over one another. Entire regions were shortened and uplifted in a single geological movement. This is planetary collapse on a grand scale, not catastrophic, but inexorable. The process did not destroy Mercury. It reshaped it slowly, folding the surface inward like the skin of a drying fruit. Unlike Earth's faults, which often show signs of repeated movement and erosion, Mercury's scarps are preserved almost exactly as they formed. There is no wind to soften them, no rain to wear them down, no vegetation to hide them. What we see today is what the planet created long ago. Some scarps cut across impact craters, proving that they formed after the heavy bombardment period early in the solar system's history. This means Mercury continued shrinking long after its surface was already ancient. The planet did not settle quickly. It kept changing. These cliffs are found across the entire planet, not concentrated in one region. This global distribution suggests that Mercury's contraction was planet-wide, not localized. The entire crust responded to internal cooling, confirming that the process was fundamental to Mercury's evolution. The existence of such large scarps also tells us something about Mercury's strength. Despite intense stress, the planet did not shatter completely. Instead, it accommodated contraction through faulting, preserving structural integrity while reshaping its surface. Mercury endured. From a distance, these cliffs add to Mercury's harsh appearance. They reinforce the sense of a world shaped by force rather than balance. A place where surfaces are pushed, folded, and broken rather than gently molded. From a scientific perspective, they provide invaluable clues. By studying their size, distribution, and orientation, researchers can reconstruct Mercury's thermal history. Each scarp is a measurement, a marker of how much the planet has cooled and how much it has shrunk. Even today, Mercury may still be adjusting. While major contraction likely occurred billions of years ago, minor movements may continue as the core slowly cools further. The planet's surface remains locked in a long-term response to internal change. These cliffs stand as monuments to Mercury's internal struggle. They are not signs of violent destruction, but of endurance under stress. The planet did not explode or collapse suddenly. It adapted, reshaping itself gradually in response to unavoidable physical laws. Mercury is a planet that has been compressed by time. It has folded itself inward, scar by scar, under the combined pressure of cooling metal and relentless solar exposure. Frozen water, hidden on the hottest planet. At first glance, the idea seems impossible. Mercury is the closest planet to the Sun, a world where daytime temperatures soar high enough to melt metal. And yet, hidden within its shadows, water ice exists unchanged, ancient, and stable. This contradiction is one of the most extreme and fascinating aspects of Mercury, revealing how temperature, light, and geometry interact in unexpected ways. The presence of ice on Mercury was not always known. For decades, the planet was assumed to be completely dry, baked by the sun, and stripped of all volatile substances. Its proximity to intense heat made the survival of ice seem unthinkable. But Mercury's environment is not uniform. Its extremes create pockets of permanence as well as violence. Mercury's axis is tilted only slightly compared to Earth's. This small tilt means that sunlight strikes the planet in a very specific way. Near the poles, the sun never rises high in the sky. As a result, deep craters in these regions contain areas that never receive direct sunlight at all. These are permanent shadows regions that remain dark through every Mercury day, year after year. Inside these shadowed craters, temperatures remain astonishingly low. While the surrounding surface may bake, these regions never warm. Heat cannot reach them directly, and without an atmosphere to circulate warmth, they remain locked in darkness and cold. In some places, temperatures stay below -170 degrees Celsius indefinitely. Under these conditions, ice can survive. Radar observations first hinted at this possibility. Bright radar reflections near Mercury's poles suggested the presence of highly reflective material. Subsequent measurements from spacecraft confirmed that these signals matched the signature of water ice. Further data revealed that this ice is buried beneath thin layers of dark material, protected from sublimation by the surrounding cold. This ice is not seasonal. It does not melt and refreeze. It has likely existed for millions, possibly billions of years. The permanent shadows act as natural cold traps, shielding the ice from Mercury's otherwise brutal environment. The source of this ice is still debated. Some of it may have been delivered by comets or asteroids that impacted Mercury long ago. When these icy bodies struck the planet, some water vaporized, but some may have migrated toward the poles, freezing permanently in shadowed craters. Another possibility is that Mercury's interior released water vapor through volcanic activity early in its history. That vapor could have traveled across the surface, eventually settling in cold traps near the poles. Regardless of origin, the result is the same. Mercury contains a hidden reservoir of ice in the last places sunlight can reach. The existence of ice near the sun underscores how extreme Mercury truly is. The planet does not average its conditions. It segregates them. Heat dominates where sunlight falls. Cold persists where it does not. There is no moderation, only separation. This phenomenon highlights a broader truth about planetary environments. Temperature is not only about distance from the sunday. It is about exposure, geometry, and time. Mercury's slow rotation and minimal tilt allow shadows to remain shadows forever. For scientists, this ice offers a rare opportunity. It preserves a record of material from the early solar system, protected from alteration by atmosphere or liquid water. In these frozen pockets, Mercury stores a fragment of its past, untouched by the planet's violent surface cycles. The presence of ice also reshapes our understanding of habitability and planetary processes. It demonstrates that, even in extreme environments, stability can exist under the right conditions. Mercury is not uniformly hostile. It is selectively harsh. As we continue, the question becomes not just how ice survives, but how these shadowed regions remain cold despite the overwhelming heat nearby. Permanent shadows and the geometry of survival. To understand how ice can exist on Mercury, we must understand the geometry of sunlight itself. The sun does not shine equally everywhere, and on Mercury, this inequality is amplified to its extreme. Because Mercury's axis has almost no tilt, the sun follows a predictable path across the sky. Near the equator, it climbs high overhead, delivering intense, prolonged heating. Near the poles, however, the sun remains perpetually low on the horizon. It never rises high enough to illuminate the floors of deep craters. These craters act like natural vaults. Their steep walls block sunlight entirely, creating environments where darkness is permanent. Unlike Earth, where seasonal changes eventually bring sunlight to almost every region, Mercury's geometry locks these shadows in place. Without sunlight, there is no direct heating. And without an atmosphere, there is no indirect heating either. Heat cannot flow sideways into these regions. The surrounding rock may be hot, but thermal conduction through rock is slow, and the distances involved are large. The shadows remain isolated. Over time, these cold traps reach thermal equilibrium at extremely low temperatures. Once cold, they stay cold. Nothing disturbs them. The sun passes overhead, but never reaches inside. Mercury rotates, but the geometry does not change. This stability allows ice to persist indefinitely. Even small amounts of ice, once deposited, remain protected. Sublimation, the process by which ice turns directly into vapor, occurs extremely slowly at these temperatures. Covered by a thin layer of insulating material, the ice is further shielded from energy transfer. The contrast between these shadowed regions and the surrounding terrain is extreme. Just kilometers away, the surface may reach temperatures that would instantly vaporize ice. Yet inside the shadows, frozen water remains untouched. This sharp division illustrates Mercury's defining characteristic. It is a planet of absolute conditions. It does not blend hot and cold. It separates them completely. The permanent shadows also reveal the importance of time. Because Mercury's rotation is so slow, the sun's angle changes very gradually. Even areas near the edge of shadow may remain cold for long periods. Over millions of years, this allows volatile materials to migrate slowly toward these cold traps and accumulate. The ice itself may not be pure. It is likely mixed with other frozen compounds, organic materials, sulfur, or carbon-based molecules delivered by impacts. These substances darken the surface above the ice, helping protect it by absorbing stray radiation before it reaches the frozen layer below. This combination of geometry, isolation, and time creates one of the strangest environments in the solar system. Ice surviving beside fire, permanence beside chaos. Mercury's polar ice does not contradict its extremity. It completes it. The planet demonstrates that extremes do not cancel each other out. They coexist, locked into place by physical law. Heat reigns where light falls. Cold endures where it does not. A world marked by ancient violence. When we look at Mercury from orbit, its surface tells a story that few other planets still preserve. It is a story written in scars, countless craters, overlapping impacts, fractured plains, and broken terrain. Mercury's face is one of the oldest and most heavily marked in the solar system, a record of violence that has survived almost unchanged for billions of years. Mercury formed during a time when the solar system was young and chaotic. Planets were still assembling, debris filled interplanetary space, and collisions were common. Asteroids and comets moved on unstable paths, frequently crossing the orbits of forming worlds. Mercury, positioned deep within the sun's gravitational well, was especially exposed to this early bombardment. Unlike Earth, Mercury had no thick atmosphere to burn incoming objects and no active geology to erase the scars afterward. Each impact struck directly, releasing enormous energy upon contact. Rock vaporized. Shock waves traveled through the crust. Craters formed instantly, locking the moment into the planet's surface. Over time, these impacts accumulated. Craters formed on top of craters, erasing older boundaries while creating new ones. Entire regions were reshaped repeatedly, yet the overall record remained intact. Mercury became a geological archive, preserving the memory of the solar system's violent youth. Some of Mercury's craters span hundreds of kilometers. These massive basins formed when large objects struck the planet at tremendous speed. The energy released during such impacts would have been sufficient to melt rock across wide areas, creating smooth plains that later cooled and solidified. These plains now sit alongside heavily cratered regions, offering contrast between destruction and resurfacing. One of the most striking features on Mercury is its global distribution of craters. Unlike Earth, where oceans, tectonics, and erosion erase impact records unevenly, Mercury shows impacts everywhere. There are no young regions spared from bombardment. Every part of the planet bears witness to collision. This uniform scarring suggests that Mercury's surface has remained largely unchanged for most of its existence. After the early period of heavy bombardment, impact rates dropped significantly. With little geological activity to reshape the surface afterward, the scars remained. The absence of an atmosphere played a crucial role in preserving this record. Without wind or rain, craters did not erode. Without plate tectonics, the crust did not recycle. Without oceans, there was no sediment to bury features. Time passed, but the surface stayed frozen in its ancient form. Mercury's extreme temperature swings further contributed to surface preservation in an unexpected way. While thermal stress fractures rock, it does not erase large features. Instead, it adds fine cracks and breakdown without smoothing the overall landscape. The scars remain sharp, clear, and well-defined. Spacecraft observations have revealed subtle differences in crater appearance across Mercury's surface. Some craters appear fresher, with sharp rims and clear ejecta patterns. Others are more subdued, their edges softened by billions of years of micrometeorite impacts and radiation damage. Together, they form a layered timeline of planetary history. Mercury's proximity to the Sun also influences impact speeds. Objects falling inward toward the Sun accelerate, striking Mercury with greater energy than they would deliver to planets farther out. This increased velocity makes impacts more destructive, deepening craters and amplifying shock effects. Each crater on Mercury is not just a mark, it is a measurement. It tells scientists about the size, speed, and frequency of impacts during different eras. By studying crater densities and distributions, researchers reconstruct the history of collisions that shaped the inner solar system. Mercury's surface, then, is not merely damaged. It is informative. It preserves a level of detail that has been erased elsewhere. It shows us what planetary surfaces looked like before atmosphere, water, and tectonics softened them. As we drift across this scarred world, it becomes clear that Mercury has endured more than most planets. It absorbed impacts, solar radiation, and thermal stress without losing its identity. Its surface remains as a silent witness to events that occurred when the solar system itself was still finding its shape. But Mercury's scars are not only ancient, some reveal signs of later activity, interactions between impact damage and internal processes that continued long after the bombardment era ended. Why Mercury looks older than most planets? Mercury's surface does not simply appear ancient, it is ancient. And unlike many other worlds, it looks its age. Where Earth constantly renews itself, and Mars shows signs of partial resurfacing, Mercury preserves the deep past almost everywhere you look. One reason Mercury looks older than most planets is the near absence of geological recycling. On Earth, plate tectonics continuously destroy old crust and create new surface. On Venus, volcanic resurfacing has erased much of the impact record. On Mars, erosion and localized volcanism have altered large regions. Mercury has none of these processes at a scale sufficient to refresh the planet. Its volcanic activity largely ceased billions of years ago. Its crust cooled and thickened. With no active plates and no erosion, the surface entered a state of geological stillness. This stillness allows impacts to accumulate without being erased. Each new crater adds to the record, layering history rather than replacing it. Over time, the surface becomes increasingly saturated with craters, giving Mercury its heavily scarred appearance. The planet's small size contributes to this effect. Smaller planets cool faster, shutting down internal activity earlier in their history. Mercury's volcanic phase ended relatively early, leaving little opportunity for widespread resurfacing afterward. Once the planet settled, it stayed settled. Mercury's metal-rich interior also plays a role. The thin mantle above the core limits the amount of molten material available to reach the surface. Volcanism occurred early, filling some impact basins with lava, but it did not continue long enough to erase the global crater record. Even when volcanic plains formed, they often followed impact events rather than replacing them. Lava flowed into basins created by collisions, smoothing their floors but preserving their outlines. The scars remained, altered but not removed. The planet's lack of atmosphere further reinforces its ancient appearance. Without wind or precipitation, fine details persist. Ejecta patterns around craters remain visible. Sharp rims do not wear down quickly. The landscape retains a crispness that defies its age. Micrometeorite impacts and solar radiation do slowly alter the surface, darkening and softening it over time. But this process is gradual and uniform. It does not erase features. It merely ages them gently, like a photograph fading rather than tearing. Mercury's proximity to the Sun also influences how its surface ages. Radiation breaks chemical bonds, modifies minerals, and darkens exposed rock. These effects accumulate slowly, giving the planet a muted, weathered appearance without removing structural detail. When scientists compare Mercury's surface to that of the Moon, they see similarities. Both worlds lack atmospheres and preserve impact records, but Mercury's environment is harsher. Higher impact speeds, stronger radiation, and extreme temperatures make its surface feel even more unforgiving. Mercury appears older because it has remained exposed for longer without intervention. It has not been softened by time, it has been preserved by it. This preservation makes Mercury invaluable to planetary science. It offers a glimpse into the earliest chapter of rocky planet evolution, showing what worlds looked like before they developed atmospheres, oceans, and dynamic interiors. Mercury is not a dead planet. It is a finished one. A world that reached equilibrium early and then endured, carrying the memory of its formation on its surface. Why Mercury defies every planetary expectation. When Mercury was first observed through early telescopes, it appeared unremarkable. A small, gray world, close to the Sun, difficult to see and easy to overlook. For a long time, it was treated as a footnote in the solar system, a simple, airless rock circling too close to matter much. But the deeper scientists looked, the more Mercury refused to fit expectations. Nearly every rule we assume about planets breaks down here. Closest does not mean hottest. Small does not mean simple. Airless does not mean inactive. Ancient does not mean unchanged. Mercury is extreme not in one way, but in many, layered together in a way no other planet matches. Its orbit places it under relentless solar influence, yet its surface alternates between furnace and freezer. Its days last longer than its years, stretching time itself into something unfamiliar. Its atmosphere barely exists, yet it is constantly renewed and stripped away in an endless cycle. Its interior is dominated by metal, heavier than a planet of its size should allow. Its surface is scarred, folded, cracked, and preserved like a fossil of the early solar system. Each of these traits alone would make Mercury unusual. Together, they make it singular. What truly defines Mercury's extremity is not intensity, but imbalance. Most planets settle into some form of equilibrium. Earth balances heat through air and water. Venus traps heat uniformly. Mars lost heat and activity gradually. Mercury never stabilized. It never found balance. Instead, Mercury exists at the edge of multiple thresholds. The edge of atmospheric retention, the edge of magnetic survival, the edge of geological endurance, the edge of thermal tolerance. It is a planet constantly pushed toward extremes, yet never fully crossing into collapse. This makes Mercury a natural laboratory for planetary physics. By studying it, scientists learn not just about Mercury, but about the limits of rocky worlds everywhere. How close can a planet orbit its star before it loses everything? How much metal can a planet contain and still behave like a planet? How long can a surface remain unchanged without atmosphere or tectonics? Mercury answers these questions quietly, through evidence rather than activity. Its weak magnetic field reveals how small planets struggle to protect themselves. Its polar ice shows how stability can exist even under extreme heat. Its cliffs record the slow contraction of a cooling world. Its craters preserve a memory erased on more forgiving planets. In recent decades, spacecraft have transformed Mercury from a mystery into a messenger. Each close pass revealed complexity where simplicity was expected. Each measurement contradicted assumptions made from afar. Mercury is not extreme because it is chaotic. It is extreme because it is precise. Every process operates exactly as physics dictates, when nothing intervenes to soften the result. No air, no water, no recycling, just exposure, gravity, heat, and time. And time, on Mercury, has been merciless. For billions of years, the planet has endured conditions that would destroy less resilient worlds. It has not adapted in the biological sense. It has not changed direction. It has simply persisted, carrying its history openly on its surface. Mercury is the solar system stripped to fundamentals. And that is why it matters. Mercury as the solar system survival test. Final outro. As we come to the end of our journey, Mercury no longer feels like a distant curiosity. It feels like a boundary, a line drawn by physics that shows how far a rocky planet can be pushed and still remain intact. Mercury survived where many worlds might not have. It survived the sun's early violence. It survived the loss of its atmosphere. It survived internal collapse. It survived billions of years without renewal. In doing so, it became something rare, a planet that remembers everything. Where Earth constantly forgets its past, Mercury preserves it. Where Venus resets itself, Mercury records. Where Mars partially fades, Mercury endures. This endurance does not come from protection, but from acceptance. Mercury does not resist its environment. It yields to it completely. Heat is allowed to burn. Cold is allowed to freeze. Impacts are allowed to scar. Time is allowed to stretch. Nothing interferes. This makes Mercury one of the most honest planets we know. Its surface tells the truth about planetary formation. Its interior tells the truth about cooling worlds. Its orbit tells the truth about gravitational dominance. Its extremes tell the truth about proximity to a star. In the search for exoplanets around distant suns, Mercury-like worlds may be common. Small, dense planets orbiting close to their stars, exposed to radiation and tidal forces. By understanding Mercury, we gain insight into countless unseen worlds across the galaxy. Mercury shows us what happens when a planet forms close, loses quickly, and endures anyway. It is not a failed planet. It is a completed one. As the sun rises slowly over its horizon, lingering for weeks at a time, Mercury does not respond with storms or clouds. It responds with silence. The surface heats, the rocks expand, time moves forward. And when night finally arrives, the heat leaves just as quietly. Cold settles in, shadows deepen, ice remains hidden where light never reaches. This rhythm has continued for billions of years. It will continue long after humans are gone. Mercury does not change for observers. Observers change while Mercury remains. And in that stillness, beneath the overwhelming presence of the sun, the most extreme planet in the solar system, simply exists unshielding, unprotected, and unforgettable.